Good morning, everyone. I'm Tiago Sousa, and today I'm excited to share with you the initial research conducted as part of my doctoral work, which focused on the formal verification of ecosystem restoration requirements using UML and alloy. Um, I'm, I have to say that this presentation is the result, or well, the presentation of this paper is the result of teamwork led by Professor Nicolas Guelfi and Dr. Benoit Ries, who unfortunately could not be here today. Um, to begin, it's important to dive into the motivation behind our research. So it's no secret that ecosystems are the lifeblood of our planet, and they play a pivotal role in sustaining human life. The Stockholm Declaration, which was adopted in 1972, recognized the need to protect the environment and acknowledge the impact of human activities on the environment. However, human activities continue to grow and to introduce significant disturbances that damage the equilibrium of natural ecosystems and their ability to function normally. As a result, nowadays ecosystems are facing unprecedented threats due to climate change and environmental degradation. And because of that, ecosystem restoration has evolved beyond the simplistic goal of returning them to their prior states. It now requires taking climate change into account. Given the significant and ongoing impact of human activities on ecosystems, there is an increasing need for modeling and predicting the resilience of ecosystems. I think it's normal because I'm sharing with my Zoom account here. Sorry, quick issue here. So I was saying that given the significant and ongoing impact of human activities on ecosystems, there is an increasing need for modeling and predicting the resilience of ecosystems, as well as promoting ecosystem restoration efforts. This will allow to assess ecosystem vulnerability and support stakeholders such as researchers, data scientists, and policymakers in improving algorithms and implementing conservation management and, of course, restoration strategies. This need arises from the understanding that resilient ecosystems can effectively mitigate and buffer the impacts of disturbances, including those caused by anthropogenic activities on biodiversity and, of course, the overall sustainability of our planet. And this is extremely particular in today's context, as it not only focuses on preserving existing ecosystems, but also emphasizes the restoration of degraded ones, which ultimately contributes to a healthier and more sustainable environment. But in a society where software is king, developing software systems to facilitate ecosystem restoration is far from straightforward due to the inherent complexity of these systems. You might be thinking, well, how complex can it be? Well, let me say that first, ecosystems are highly intricate and dynamic systems with numerous interacting components, species, and ecological processes. Capturing the full complexity of these systems in software requirements can be extremely daunting. Second, ecosystems are influenced by a wide range of natural factors such as climate, weather, seasonal changes. And so incorporating all those different variables into software requirements to accurately model ecosystem behavior is a complex challenge. Moreover, gathering relevant data for ecosystem modeling and restoration efforts can be arduous. Integrating data from diverse sources and formats into software applications requires careful planning and design. And this task is even more complicated since ecosystem restoration requires collaboration between different stakeholders such as ecologists, biologists, data scientists, and of course, software developers. among different stakeholders. And finally, there is often uncertainty in ecological science, which includes gaps in understanding of ecosystems function. So this can make it difficult to define precisely software requirements for ecosystem restoration. Um, uh, Nevertheless, based on literature review, we have found that model-driven engineering has the potential to significantly contribute to address the mentioned challenges. Therefore, our research question is, how can model-driven engineering contribute to specifying and verifying ecosystem requirements models? A little bit of background. So prior research highlights the importance of modeling languages and formal methods across domains. The unified modeling language has become the de facto standard and has been applied beyond software to areas like environmental modeling and sustainable ecosystem management. In terms of formalization, well, it remains relatively limited in the ecosystem domain, likely due to the complex and often nonlinear nature of ecological systems that, of course, creates challenges for applying formal techniques. I will now present the first activity of our approach, namely the requirement specification of ecosystems. This activity aligns with the initial stages of a simplified waterfall software engineering lifecycle, namely the requirements engineering phase. This phase is crucial as understanding and managing the intricate relationships between various entities and properties is pivotal for the success of ecosystem restoration efforts, as discovered from literature. So efforts are crucial for ecological health and sustainability. Our paper contributes with the first version of a specialized metamodel specifically designed to capture and analyze the complex relationships within ecosystem restoration requirements. This metamodel provides a semi-formal framework as depicted in the figure, which allows us to comprehensively abstract the relationships and factors involved in ecosystem requirements. Moreover, it serves as the foundation for our approach, allowing stakeholders to make informed decisions related to ecosystem restoration requirements. I will now present two core concepts of the meta model, and we shall begin with the concept of an ecosystem. So, in our approach, an ecosystem represents a complex ecological system consisting of various species, regions, restoration goals, and potentially nested sub-ecosystems. This kind of abstraction allows us to capture the organization, the complexity, as well as the interrelationships of the components within a natural environment. In our meta model, you can see that the ecosystem class, which forms associations with species, region, restoration goal, and even as a recursive association with itself or a sub-ecosystem. These relationships helps us model the diverse aspects of an ecosystem and the different interactions with different components as well. Literature has shown that ecosystems are much faster than what I present here, but of course, my objective was to create an abstraction where we could define ecosystem restoration. Therefore, some concepts related to ecosystems, such as food chain, are not taken into account in this specific meta model. Another core concept is the concept of property, because in every ecological restoration process, there are key properties which impact the overall restoration. Therefore, in our ecosystem requirements model, a property represents the key factors, the conditions or characteristics associated with an ecosystem. These properties play a crucial role in understanding the ecosystem's health, restoration, or degradation. And so, by capturing and analyzing these properties, stakeholders can gain valuable insights into the ecosystem's current state and assess the impact of specific interventions or strategies for restoration, conservation, and management. Within our metamodel, you can see the property class, which serves as a representation of different attributes and characteristics of an ecosystem, and each property is associated with a particular origin and type, allowing us to classify them based on their nature and function within the ecosystem. These properties are associated with the restoration goal and property type classes, which allows us to understand how they relate to the restoration goal of an ecosystem. Literature review has shown that understanding and effectively managing properties within an ecosystem is fundamental for making informed decisions in restoration projects. Now that I presented the ecosystem requirements specification, I will transition into the formal verification aspect of our framework, of our approach. I will start by quickly presenting the translation from UML to Alloy. But I think first it's important to clarify what exactly formal verification is, as some of you might not be familiar with the topic. So formal verification is a mathematical approach to assess the correctness of a system model. It involves using logic and formal methods to prove or disprove properties of a system model, of course. In our case, we apply formal verification to ecosystem restoration requirements to ensure their accuracy. Our approach provides a semi-formal framework for modeling and understanding ecosystem requirements, which was the metamodel that I just presented. But as software systems become more complex, the need for robust verification and validation techniques grows increasingly important. So we leverage Alloy to transition from semi-formal to formal representation of ecosystem requirements. Alloy is a formal modeling and specification language that is designed to help us express complex software systems with precision and clarity. The benefits of using Alloy are substantial. First, it helps us catch design flaws and inconsistencies early in the development process, which reduce the likelihood of costly errors down the road. And additionally, it's also an excellent tool for validating requirements and creating formal executable documentation of system behavior. Finally, Alloy has a broad scope of application, and it's widely used in software engineering, formal methods, and research to model and analyze software systems of different complexities. In our approach, we have translated our semi-formal UML metamodel into Alloy. The translation ensured that our formalization aligns with our original ecosystem requirement specification, and we map UML concepts such as classes, attributes, and relationships to Alloy signatures, fields, and constraints. Therefore, in our approach, each metamodel concept becomes an Alloy signature with the associated fields and constraints. I have to say that in the paper, we have systematically presented the formalization of the different key concepts. But in this presentation, we focus only on the ecosystem concept formalization. So how can we formalize the ecosystem concept? First, in natural language, our definition of an ecosystem is a complex ecological system comprising diverse species, regions, and possible sub-ecosystems with associated restoration goals. To formalize it, we define the signature in Alloy named ecosystem, which includes some attributes. So the first one is the attribute as species, which is a set of species within the ecosystem. The second is region, which is a set representing different geographical or ecological regions within the ecosystem. The third one is restoration goal, which is an optional element indicating a specific objective related to ecosystem restoration. And the fourth one is sub-ecosystems, which is a set of possible sub-ecosystems nested within the main ecosystem. Additionally, those on this signature to ensure that there must be at least one region within the ecosystem. Therefore, the number of regions shall be greater than one, or greater or equal to one, and the ecosystem can contain 0 or more sub-ecosystems. So the number of sub-ecosystems shall be greater or equal to 0. This formalization allows us to precisely model and reason about ecosystems within the context of the alloy specification language. And the last activity of our approach is the verification of safety and liveness properties. For those of you who might not know, safety properties ensure that undesirable situations do not occur. In our case, I have to say that safety properties ensure that undesirable situations do not occur in the restoration process, while liveness properties ensure that the natural ecosystem progresses towards the desired restoration goal. In our approach, different safety and liveness properties are checked using the alloy analyzer to verify the results of an ecosystem restoration. We examine instances of our formal model where properties are violated to identify potential issues or inconsistencies in the model and to refine it accordingly. This iterative process improves the reliability and the robustness of ecosystem restoration requirements. The benefits of following this process is that it helps ensure the accuracy of restoration requirements, reduce errors, and ultimately contributes to the success of restoration projects. So, for instance, in the figure on the right side, 2 different properties have been checked with the alloy analyzer, which is a tool to verify properties with the alloy specification language. And as you can see on the right side of the figure, the output reveals that no counterexamples are found for both properties, which indicates that the assertion might be valid within our formal model. Now I will quickly talk about the related work. If we focus on the modeling phase, apart from the other works I already presented at the beginning of the presentation, we found that Keiter et al. Introduced a non-formalized UML metamodel, which was specific to environmental software modeling. They used UML to model the internal function logic of each component in their framework. If we compare in our approach, on the other hand, we apply a semi-formal UML metamodel for ecosystem restoration, and we formalize it using alloy to be able to leverage the strengths of both approaches to create a more robust and reliable models, specifically within the context of software engineering. Now, regarding the formalization related work, we found some papers where formal methods have successfully been employed within the ecosystem domain. For instance, Thomas et al. Applied model checking techniques to assess the dynamics of ecological systems, providing a clear methodology using state transition graphs and temporal logic formulas. Similarly, Königsberg presented a formal methodology for modeling and verifying predator-prey interactions, demonstrating the power of first-order logic and qualitative methods in addressing ecological questions. And lastly, Larguet et al. Proposed a qualitative modeling approach using timed automated formalism and model checking techniques to evaluate ecosystem property dynamics and temporal evolution in response to management options. We shall turn our attention to assessing the strengths and limitations of our approach. So, as the first strength of our approach is the ability to identify consistencies and errors at the early stages of the software development lifecycle. This proactive error detection can save valuable time and resources in the long run to the different stakeholders. Our formalized metamodel also improves the clarity of communication among stakeholders, and this precision reduces the ambiguities and increases confidence in the validity of ecosystem requirements. Clear communication is essential for the successful implementation of any project, and our approach excels in this regard. In terms of limitations, however, the use of alloy, while powerful for formalization and verification, can create some challenges as it can be extremely complex to use and often require a significant learning curve for stakeholders. An additional limitation is the scalability of alloy, because as the requirements for ecosystem restoration becomes more complex and vast, the performance of the alloy analyzer, which allows us to verify the different properties, might degrade. Therefore, we need to address scalability issues to ensure that our approach remains viable as ecosystem restoration requirements evolve over the time. So to conclude, our work introduces a robust and new approach for modeling and verifying ecosystem restoration requirements, which effectively bridge the gap between UML and alloy. This approach significantly improves the rigor and reliability of requirements engineering and verification in the domain of ecosystem restoration, which ultimately provides invaluable insights for different stakeholders, such as researchers, practitioners, and policymakers. That's all. So thank you. And if you have any questions, please let me know.